All right, so taking a look at our next lesson, the idea of this lesson is, hopefully, for my students, you have actually completed the lab involved, although in the future, maybe we wouldn't have time for it and we might have had to overlook it. So we're looking at fluid mechanics and applying the ideas of pressure, and today we're actually going to begin looking more closely at pressure, introducing an equation for it, one of our key equations, and then setting the stage for our further studies with the mechanics of fluids. But in order to set that up, hopefully what I have, or at least what my intention was in the progress of things, was a lab, an introductory lab to get an idea of the differences between pressure and force. My experience has been many students, and many people for that matter, have a hard time actually teasing out the differences between them. They are not the same thing, though I've heard many students use those words interchangeably. Here, since we're going to be studying fluid mechanics and needing to talk about pressure specifically, we need to have a deeper understanding to know how it is different than force. And so this is an example of a little bit of a lab setup, although currently in my lab we don't actually use these containers. We actually just spread two lab tables apart and then hard clamp this is just regular paper towels. We hard clamp them over the opening there to get the same result. Tape, I think, is going to hold all right for it, but I haven't actually collected data on this and haven't necessarily got good results. But I wanted something that I could show here in the video in the event that either you missed that lab or aren't doing that lab for whatever reason, so that you could get an idea of what the difference is. This is something that you could try at home, taking basically a piece of paper towel and putting it over an opening such that you can push down into it. Now, there's a classic science fair experiment where you basically test how durable paper towels are by putting them across an opening like this and then putting like pennies or something on them and seeing what the maximum weight is that they hold until they break. It's common to also do that when they're wet to check, hey, which ones are the toughest, that sort of thing. Not actually our goal. Our goal is to get a distinct, hopefully, feel between the difference between force, which is a thing that we've studied quite a bit, and hopefully developed a good understanding of, that's a push or pull on something, and the idea of pressure. Now, if you go further in solid mechanics studies, you'll find that breaking points of different materials are measured in the same units as pressure, and they're directly related to pressures. So the idea being rope, for instance, if it's very thin, very small area, as we're going to see, it might break under much lighter forces or much lower forces, as opposed to thicker areas. Basically, the size of a thing has a direct effect on the breaking point. And that's what this lab is supposed to get across. Now, as of the filming of this video, we are short on actual digital force probes, but we do have our delightful smart carts here, and we can activate those, tie them to our software, and turn on the force sensor that is built into them. So in a bind, we're actually using the force sensor of the smart cart, not actually the motion sensor, in one of our very few labs to do that. I've also attached to the force sensor the little rubber bumper on there, and that's more so it can easily interact with the materials that I've got. So the other things that we've got for that lab are a series of wooden circles. I've got the tiny one, the small one, the medium, large, all the way up to extra large and huge. Now, these large, especially large ones, they start having more of a sharper edge, so their data may not necessarily agree as well with some of the smaller ones. And we're going to find the equation that I'm going to introduce is not actually going to perfectly match the equation or what we see from this lab, but the lab still shows us an important idea, really emphasizing the difference between force and pressure. Now, I'm not going to turn on the force sensor on this. Again, take a look at the video that I have for the lab associated with this, or give it a try yourself, and without having the actual numbers, at least feel the difference. Because that's one of the big things that we want you to understand, is being able to tell that difference. Not just numerically, which is good, but also so that you can see the differences. So I've got the tiny circle, and I'm going to turn on my smart cart, get it connected, or my force probe, I should say, and have it where it's going to read the force output, and this is where when you hit the breaking point, the force scale will immediately drop, and you'll be able to get the maximum value on that. But on this, even if you don't have fancy equipment, just kind of take a small circle and push, and just kind of estimate how hard you have to push to actually break it. I don't know off the top of my head, that may have been about, I don't know, maybe about 10 pounds worth of force. So that was with the tiny one, and I ended up tearing the paper towel. Now it'd take a little while to pull that off and reset it, so I've got a second one here, and instead I'm going to go up to, I'm just going to go up to the large. I could go up to the extra large or the huge, but like I said, those have a little bit sharper edges. This one isn't quite as smooth as the other, but those edges can cause an effect and throw off your data. So I'm going to hold this here and I'm going to push down and get a feel for how hard I have to push in order to do that. I might estimate that this has gone up to maybe about 20, 25 pounds, but that becomes a little bit tricky to kind of estimate as you're pushing it itself. That's why if you want to get actual data on this, I do recommend having a digital force probe of some kind so that you can look for the max value on that. Regardless, one of the big things that I want with this lab is not so much to get good data that's going to reflect the equation we're about to introduce, because it won't for a variety of reasons. Maybe I'll make another video about that, but that's not pertinent to the materials that we're covering for the scope of this class. Now, if you go on further in your studies and go into solid mechanics, and looking into breaking points, yield stress, all of that, then you'll take a deeper dive into it. That being said, the results that we've got don't necessarily follow an area base, as we're about to see, but they do seem to follow at least mostly a linear base. And I have some ideas on why that might be. Regardless, the point of this lab, though, is to get hands-on and feel for the key difference between pressure and force. Because a lot of people would say you'd have to push hard enough to break the paper towel. Well, how hard I have to push, it turns out, depends on my contact area. And that's one of the key things that we want to emphasize with that lab. Whether it fully supports the equation I'm about to write on the board or not, it is still giving you an idea that it's not just force when it comes to, well, in particular, breaking points and other things that we find it is best kept track of with the idea of pressure. So that brings us to our actual lesson. Pressure. Okay, so what this is the best description of it would be, let's see, force applied over an area. Applied to or over an area. I'm being careful with the over because I'm not actually putting a force on all individual points on this. Over kind of implies that you're doing the whole thing, but when it interfaces with the other object, basically that force is being generated by the entire surface here. And so, taking a look, force applied to an area or over an area. Now, this is especially useful in fluid mechanics, but it isn't just in fluid mechanics. Like I said, for solid mechanics, even when you go into solid objects, you will find that pressure becomes, or things related to pressure, become very important for the mechanics of solids as well. That being said, that's usually a little bit more of an advanced class, more than just the intro physics class. And the intro physics class will usually start with fluid mechanics, which is the focus of this. Okay, so our main equation is going to be, the way that I always learned it, it's pressure equals force divided by area. Now, another way that this could be written, which might be a little bit more precise when it comes to the vectors, oh, sorry, not pressure, but force equals our pressure times our area. In this case, one of the things we're going to talk about is pressure is functionally a scalar. It doesn't have a direction in and of itself. And so this is the equation that I'm used to seeing, and I believe is on the current version of the AP equation sheet. It's also the one that I'm going to predominantly use in class. However, I will point out that area vectors, if you've studied those, an area does have a vector, and it points as a normal vector, 90 degrees off of the surface itself. We will find that the force that is generated by applying a pressure onto an area will do so perpendicular to the area itself. Now, that is something that you kind of need to be familiar with for the introductory class that we have. That being said, I won't necessarily go into the details of an area vector and all the vectors associated with that. Though, since we're introducing the materials, I figure I would generate or show that here. In this case, we multiply both sides by area, and we get force equals pressure times area. In this case, our pressure, P, pressure, F, force, usually applied, or the force generating the pressure, or the force generated by the pressure. But in this case, force associated with pressure. And small note on this for my handwriting, since this isn't a lined board, I'm putting a little bar on the bottom of the P to let you know that this is a capital P, which is usually how we keep track of pressure. A lowercase p is used in another unit of ours for introductory physics, which is momentum. And so I'm trying to emphasize the difference between capitals and lowercases. You've probably seen that a little bit with the various videos and lessons that we've got. But just to reiterate that in case this is the first lesson that you're jumping in on. Now let's see. This is the force associated with that pressure, and then A is the area pressure is applied to. or to which it is applied. But in this case, I'm keeping it shorthand as my notes usually are. We're going to introduce some units on this. So in the best, or in the SI approach, I should say, not necessarily best, but the one that is most likely to show up in the introductory class and geared towards the AP exam, we've got forces, of course, are measured in newtons. Areas, this is one where that could fluctuate some, where you might end up with centimeters squared or values in centimeters, that sort of thing. But the SI unit for area would be meters squared. And therefore, pressure is going to be equal to a Newton divided by meters squared, which is a Pascal. So I could put the little capital thing under there, but usually when I have a big P and the little a, that implies that it's capital. So I probably will get lazy on that one. It's usually just the P by itself that I'll actually underline. So in this case, we've got the Pascal, which is our SI unit for pressure. So the Pascal is abbreviated capital P, lowercase a, and it is equal to, a Pascal is equal to a Newton divided by a meter squared. Okay. I'm also going to bring up through the course of this lesson other common units that are used for pressure, although this and kilopascals are the ones that are going to be probably preferred by the AP exam and many introductory physics classes, especially those using the SI system. Kilopascals are not actually the SI unit, but pressures end up usually in a large value, as we're going to see. And so it's not uncommon to measure those in kilopascals. Some of the things that I had mentioned before, like breaking points, ultimate tensile strengths, that sort of thing, are often measured in megapascals or gigapascals, so very large numbers for these. Okay, so in this case, 1 Newton is actually about a quarter pound or so that's not very much force. And on a square meter is a very large thing. So small thing divided by a very large thing gives us a very small thing. 1 Pascal is actually really, really tiny, but it is the SI unit. Okay, so here's how we make those. Now that we've got that. Okay, so a common application of pressure is going to be in, well, atmospherics. So okay, so here we're going to talk about kind of the causes of pressure, at least for fluid mechanics, which is the primary focus that we've got here. The one that I showed you originally with this lab would be more of a solid mechanics, although you could still explain that on the very small level as well, though that's beyond the scope of our class. On the molecular level, so one of the things that I want to bring up is atmospheric pressure. So many of you come to me from the waking nightmare that is chemistry, and you have learned that the pressure is 1 atm or 1 atmosphere. We, for the most part, don't use those units here in at least my introductory physics class. And to my recollection, I don't think that I've seen them on the AP exam, at least any time recently, AP physics that is. Maybe it's used on the chemistry ones. Mainly because atmospheres is not the SI unit. That being said, it is a very useful unit because it's defined around kind of what the standard value, more or less, for atmospheric pressure was or is at sea level, at constant or standard temperature, and, well, I can't say pressure because that is the pressure. I don't remember all the details on the definition of it, but we've got 1 atmosphere, which for our purposes, the most important number is going to be 101,300, and I think 25, but I'm just going to keep it to 4 significant figures here. It's a little over 101,000 pascals. Or writing this differently, it is also common to see this as 101 kilopascals, where kilo means 1,000. There are also a few others that I'm going to bring up. 14.7 psi, which is pounds per square inch. So this is a common one if you're dealing with imperial or American or English system. Pounds per square inch, PSI is actually a pretty standard one. My car tires, I think, are rated to go up to about 30 PSI, so about 2 atmospheres gauge pressure, as we'll talk about in a later video. But we've got 14.7 PSI, we've got, I think it's 1.01 bar, if I remember correctly, and then 760 millimeters of mercury, which is also 760 torr. I think those are kind of interchangeable, if I'm not mistaken. I'm not going to go into all the details on this. For us, we are going to primarily talk about specifically the SI units, so 101,000 pascals or 101 kilopascals. Many of the meteorology stuff, like whenever I look at what the pressure is outside, it's usually in things like millimeters of mercury or inches of mercury. I don't actually know that number off the top of my head. And then another one that is common if you go to one of the metric countries, instead of kilopascals, they would actually describe this as, I believe, 1,000 and about 13 hectopascals. I think it's a lowercase h, I can't remember, but hecto, it's one of the few places where hecto shows up as a prefix, so I figured I'd mention it. All of these can be useful in their own way. Depending on what things you go into, you might preferentially use one versus the other. So for instance, I worked in microscopy for a while, and with our electron microscopes, we had to get things down to very low pressures. Dealing with the mech pumps and the things associated with that to get those low pressures, we would actually talk in terms of torr. Torr was kind of the standard for the pumps that we used for our specific equipment. Each of these will have different applications. Chemists often use atmospheres, but again, roundabout way of saying our primary approach is going to be this, but here are some other common numbers with that. So what does that mean? Okay, well, atmospheric pressure is, I'm going to latch on to this one because at least for many of the viewers that I think that I have, they're going to be most familiar with this. 14.7 pounds per square inch. Inch squared. Okay. So, true story, I was actually clearing out my storeroom when I first got this classroom, this job, and I came across something. In fact, here it is. It was a big, heavy piece of metal, and I was confused by it. I was like, is this just leftover robotics parts? And then I noticed something on it. There's a sticker over here, kind of faded. It says 14.7 psi, 29.9 inches of mercury, so there it is in inches, 760 millimeters of mercury, and 1 atmosphere. And I was very confused on it. I was like, why does it have a bunch of stickers for atmospheric pressure? And then I realized what I was looking at. So this is a big heavy bar. It's just under 15 pounds. In fact, I put it on a scale and it comes up to 14.7. And the edges of it are 1 inch by 1 inch. So what I want you to think about is this. It's not exactly the same, but I'd estimate this to be about the size of a nickel. Take a nickel, put it on your hand, and put a 15-pound weight or something very close to that on there, and get a feel for what that is, because that's very, very heavy. That's the pressure on your hand. Now, this demo, if you're in my class, I'll pass this around or have it where people can actually try this, though it is kind of heavy. It's about 15 pounds or so. But it's a great way to get a feel for what the atmosphere is doing to you right now. And that's something that usually surprises a lot of people because we're so used to thinking that the atmosphere, well, air is literally a lightweight, but it's actually squeezing you very, very hard right now with just under 15 pounds for every square inch of your body. And that's a lot. Let's talk about the molecular cause of this. And part of this is our pressure is going to be dependent on a number of factors, ideal gas law notwithstanding, once again, the waking nightmare that is chemistry, but also part of my physics class in the AP2 materials. So we've got the following. I want you to imagine that we've got, say, a container, a box. And on the outside of it, we've got all these little air molecules. And you may have learned in your chemistry class that these air molecules are all moving around very quickly. Some of them are moving this way, some of them this way, some of them this way. They're just kind of all bouncing around all over the place. And how fast they go is based on their temperature. More temperature, more energy, and thus they have more kinetic energy and move around. Well, what happens is if you've got one that's flying along like this, it's a very small particle, not much mass to it, but it's flying along at a very high speed, usually several hundred meters per second, so better part of 1,000 miles per hour, for want of a better term, to put that in perspective. But they're moving very, very fast in the room that you're likely in and in here. And what happens is when they run into the side of the container, they have to hit it and bounce back off. Now, we're going to learn a little bit more about this. This is what we call an impulse, which changes the momentum of that air molecule. Even if it bounces off at the exact same speed, we change its momentum because momentum is a vector. That's in some of our other lessons. Check out the lessons on momentum if you haven't already. But in this case, we have a force that must be applied onto this tiny little particle in order to change its motion. Here's Newton's laws of motion. We got a thing that's moving along, and it will continue moving at a constant speed in the same direction forever unless a force is applied to it. That even applies on the molecular level, give or take. So it hits the wall and bounces back off. And this is basically the equivalent of, like, imagine a raindrop, where if you've got one of them, you can really feel just the one raindrop, except this would be a very, very small amount of force because there's only one very tiny atom or molecule. But in this case, this isn't the only one. There are billions upon billions of them, and many of them are hitting the sides at the same time. It's kind of like instead of one raindrop, which you might not necessarily feel, having an entire bucket of water or a billion raindrops hit you at the same time, you're being hit by a solid wall of water, it feels like. And that's basically what we've got here. And that is actually happening on this side, but it's also happening on this side. So we've got, for the most part, because the air is hopefully pretty uniform, at least relatively, we're going to have just as much bouncing on this side as there is on this side. Well, if this container wall is applying a force onto the air molecule that way, then by Newton's third law, the air molecule must be applying a force onto the container back the opposite direction, equal and opposite. They're exchanging, they're interacting with these forces. Same thing happens over here. So basically, we've got that the air is bouncing up against this and basically squishing the thing as it goes. It's also bouncing into the top and then onto the sides. The one thing that it might not necessarily is if it's on a container, although that gets a little bit trickier. Imagine this just open in open space, and we'd also have ones bouncing into it on the bottom. Basically, air is bouncing into this on all sides. Now, that might result in crushing the container if it's not strong enough, or, except the container also probably has air inside of it too. And if that air is at the same temperature, it's all moving the same directions as well. Except this time, they're going to interact with forces that then try and push the thing outward. Well, in this case, as long as you have equal amounts on the outside as you do on the inside, and they're both at equal pressure, the amount that they're actually hitting with, then these two, one's basically pushing inward, one's pushing outward, and then you end up with it being held in place. Now, the reason that I want to bring this up is to emphasize the following. Classic display. This is a simplified version, well, in some aspects, otherwise it's directly the same, of something called a Magdeburg plate. Now, these are clear ones, so you can kind of see what's going on here. I've got a little rubber O-ring that I've got that fits into a groove to make this airtight, and we've got little handles. Now, if I squeeze this here, I'm going to draw this out as a diagram. I want you to imagine the Magdeburg plates as two little cups that I've got, and I can actually put them right up close together. Now, remember, there's actually a cut here. So, as long as I've got air on the inside, and I've got air on the outside, and I would end up with the following. The air on the outside is applying a force like this, or it is applying a force on the molecular level. The air overall, we would simplify it and say that it's applying a pressure, a nearly constant force over this area. Okay? But on the inside, I've also got these applying the same back out. If that's the case, then I have no net force, and this thing just kind of falls apart. In fact, you can see I can just lift this up. It doesn't actually stick together in any way, shape, or form. Now what I've got is a small air chamber in here, and I've got a hand compressor that I can use to actually set this up. Give me just a moment while I connect this up for our demonstration. And so, I've got my hand container here, and my hand pump, I should say. You can do this. This is classically shown by having a large mechanical pump and kind of hemispheres, two metal half spheres that you can put together. But I like showing it this way. What I'm doing is I'm going to pull here, and this is actually drawing air out from in between these two. In fact, I pulled this once, and we've already got it where I no longer have to hold this. This is now holding its own. So I'm going to set this aside onto the ground here, and I'm going to really try and pump as much of the air out as I can. So what am I doing? I'm reducing how much air is in here. And if we went to an extreme and said that there was no air in here, then we would end up with the following. The less air that I have in here, if I've only got just a little bit of it, then not near as many are hitting the outside edges as before, and we might end up with a little bit of pressure, but not much. And therefore, we would end up with a greater pressure on the outside, greater force as you apply that pressure over the area, squeezing these together. So I'm going to take these, I'm going to try and, I'm really going to try and pull the air out. Now I'm doing this with a setup that I've got where I built in a couple things called check valves that actually seal this up. And then I'm going to change a valve here so that I can disconnect this. I've had problems with these breaking before. because I didn't have a valve installed. So now that I've got this, instead of having the whole thing kind of loose, I've got the following. So not only does it hold its own, but I can try and pull this apart, and I can't. Maybe if I try really, really hard. Now I'll go ahead and say this because other people who have played with these, if you've got really smart students, what they'll do is they'll put it up against their chest and then use their collarbone to actually, as kind of a pivot, a lever action to pull these apart. So don't be surprised if you make one of these and give it to students, they might be able to take them apart. However, that's actually going to be the next thing that we're going to take a look at in just a moment. We're going to try and predict how much force it would take for me to pull these apart, and we'll test our equation. Now, right now, all I've got is I've drawn the air pressure in here. It's not a complete vacuum. I am not able to pull that good of a vacuum with just a hand pump made out of a syringe and very cheap check valves. But I've got very low amount of air in here, which means much lower pressure. And now the external pressure is holding these together. All I'm fighting against right now is air. Air is not the lightweight that we think that it is. Now, many people erroneously say that I pulled a vacuum in here and it's actually sucking these together. Science doesn't suck is the important phrase that I usually repeat in this section, because there's nothing about this that causes suction. We've just got a higher pressure on the outside that is squeezing this together. Now what I'm going to do is I'm going to break the seal. I'm going to turn this. We heard a little hiss, and I felt these actually come a bit farther apart as I reintroduced a whole bunch of air. Why did that happen? Because this is low pressure, so if I open up a little line, then air will run in because there's low pressure here and high pressure out here, so it will be pushed in there, and then that brings us back up where these become better balanced. And when I do that, I can pull these straight apart. They won't hold together at all. All right, to further emphasize that, and in fact to tie some of the things together, I've got the following. I've got a just cheap water bottle, and I've got the 14.7 PSI thing. What I would probably want to do, got to be careful not to hit my own projector. I can put this here. I think I can lift this up, and hopefully you're able to see this, but if I put this here, it just crushes the bottle super easy. Like there's no resistance to it effectively at all. This is a very lightweight bottle, not very rigid, not very strong, but it is containing air, not dissimilar to this. So here's what I'm going to do. I have drilled into its cap a little pressure container, just the same as we had here. And what I'm going to do is I'm going to connect this up. And we're going to see, I'm going to do the same thing that I did with the Magdeburg plates, except these are nice and thick and rigid. They can withstand the high forces that we're about to find, whereas this bottle cannot. And all I'm going to do, this is just going to allow me to pull some air out. I will not be able to pull all of it out because I'd need a high-level pump for that. Trust me, I know from experience. But let's see what this does. So I've got this ready to go. We can see that I can crush this bottle. I'm not actually crushing the bottle. This is actually super simple for me. All I'm doing is I'm pulling some of the air out of there with this pump using the check valves is the technical term for them. But I basically, every time I draw this out, I pull some air into there. And then when I push it back, I eject it out the other side here. So I've got a little handheld pump. And you can see I can squish this bottle with very little effort, just the same as that bar could do. Setting the bar on it would crush this with very little effort. Very little effort. I've gotten this crushed because of atmospheric pressure. All I've done is reduce the pressure in here and then let the air crush it. But as soon as I break that seal, we can see that it spreads back out a little bit. Now, that's one of the things that I've actually got. I don't think I brought it over here. I've got, this is my hand pump that is marked pull, because I'm pulling the air out, for want of a better term. And I've got another one that I've marked push, so I can actually re-inflate this to use this later. But that's the demo that I wanted to show for there. Okay. Now that we've talked a little bit about the applications and getting an understanding of what's happening on the molecular level, which is something that is commonly tested on both the AP exam and in introductory physics classes. On top of that, understanding the mechanics of what's causing this can be very, very useful for future applications as well. Okay, let's see. Let's go with I'm going to do it at the end, but I also have a Magdeburg chamber. Basically, I can use this with a chamber to put a balloon in it, a partially inflated balloon, and as I decrease the pressure in the chamber, the balloon will actually get bigger because it has air at regular pressure, and so it will push out until the volume changes to lower the pressure. There's some ideal gas law stuff in there. And if we have time, a marshmallow as well, but that'll be towards the end of this video to keep things on track. Now that we've got all this set, let's take a look. Let's use our equation to actually make some predictions here. How much force am I actually fighting against when I'm working with these Magdeburg plates? So here's what I'm going to do. I'm going to measure from one side of it to the other, at least where my groove is, where the sealant was, because that's where we can actually remove a significant portion of the air. So I'm going to say that we've got this thing, and its diameter is equal to 8 centimeters. That's about what I've got here for this. And so let's run through and do a quick calculation using our equation to predict how much force I actually have to apply to try and pull these apart. Okay, so if this is the container, I've got air pushing down on the outside of this and none pushing back out from the inside of it. So on this, here's what I want. If I want to know the force that the air is applying on this, we know our equation looks like this. Pressure equals force divided by area. Well, if I want this, I'm going to need to fill in the other values. Well, this is air. While I didn't check the actual weather today, and we're not at sea level, we'll go ahead and say that we're at 101,300 pascals is our pressure, because we've got it exposed to atmosphere on this side. So we'll just use the standard atmospheric pressure for that. Our area, well, I've got a circle here, so the area is going to be equal to pi r squared. Well, that would be pi times 0.04 meters quantity squared. Now, here's the common place where students make a mistake. Remember, all of our equations are best used by putting SI in to get SI back out. So if I want an answer in newtons, I need to use meters for my radius measurement. I've also taken diameter is 0.08 meters, that's 8 centimeters. And as a reminder to my students, and pretty much anyone in general if you're studying these things, it's very much worth your time being able to quickly and reliably convert centimeters to meters in your head. That's something that you probably want. Okay, so on this, I can then do the following. That my force will therefore be equal to my pressure times my area. I'm reworking my equation there. So we've got that our force will be equal to 101,300 pascals, which is a Newton per square meter, times our area, which I'm going to run that through. So I've got 0.04 squared, so that's my radius squared, times pi gives me 0.00503 meters squared. Okay, so when I multiply this out, 101,300, I get the following. My force on one side of this comes up to about 509 newtons. Remember, a pascal is a newton divided by meters squared times meters squared. Our meters squareds cancel out, leaving us with newtons. Here's why we have an SI system. Put SI in, get SI back out. So if you get a very different number if you use 101 instead of 101, keeping track of your units. 509 newtons, that comes up to, this is approximately 116 pounds. So when we go back up to our Magdeburg plate and we think about it, oh, let me redraw it. We've got one plate here and one plate here. They're together, but all things being equal, if I could pull all the air out of there, make this empty, so we would only have the force going in, we have this pressure being applied over our area. We have 101,300 pascals applied over an area of 0.05 meters squared. And we find that this comes up to a force, we're basically pushing to the side with a force of 509 newtons, which is about 116 pounds. But that's just on one side. We've also got, by symmetry, the exact same thing on the other, which means we're also going to have 509 newtons on this side. This thing is being squeezed together by a little over 1,000 newtons. And when we convert that over to pounds, we're going to come up with almost 250 pounds. So for me to pull this apart, I would have to pull with about 250 pounds. It's doable, but it's not that easy. Okay, this is some of the effects of atmospheric pressure and how to apply them. All right, so that's the majority of the lesson that we actually wanted to cover for the materials that we've got there. But there are a few other things that I'd like to actually go through to make certain, one, that we've got a little bit more practice, and two, to tie this to practical applications with which you might encounter depending on what you go into in the future. So the first thing that I'd like to do is force on your head, or more accurately, on my head. Right now, and this is something that we've just experienced our entire life, so we're not actually used to it. We're going to talk more about this in a later lesson about hydrostatic pressure, where you can do a comparison by diving down into a pool. In fact, when you dive down into a pool, when you go super deep, you can feel the weight of that water. You can actually feel your body being squeezed on all sides by the pressure of the water. Well, that's also happening right now quite a bit to your body from the air, the thing that we've described here. We saw it crush a bottle, we saw it hold together with a large amount of force, a very small object. And so, looking at something as innocuous as, well, we're being squeezed, and to estimate the amount of force that we would have on that, one of the things I like to do is to estimate the force on your head. Now I'm going to approximate my head as a round object. This isn't the most scientific measurement ever. Hopefully you saw it there, but it's about 20 centimeters or so. That's the diameter. So we're going to say that Sanchez's head is a circle of some kind, and that the diameter is equal to 0.2 meters. What I would like to know is, how hard is atmospheric pressure pushing down on my head? Now, part of that comes from the kinetic energy of the particles themselves, and as we will see, part of atmospheric pressure comes from something that we would possibly describe as hydrostatic pressure, which is basically, not only do I have a little bit of air above my head, but I've also got more above that and more above that. Makes the most sense if I were standing outside, but if you think about it, you've actually got the better part of 100 kilometers worth of air sitting on top of your head. You're kind of at the bottom of a giant pool of air that's about 100 kilometers deep. Although that one gets a little bit tricky because air kind of changes density and gets thinner as you go up. But we're at the bottom of a very deep pool of air. But air is pushing down on my head, and I'd like to know by how much. So let's estimate that. So we've got the following. We want our pressure equals our force divided by our area. My area in this case would be equal to pi 0.1 meters squared, which I guess my area would therefore be 0.0314 meters squared, at least close to. We know it's not a perfect measurement, but let me double check on that. 0.1 squared times pi gives me, yep, okay, great. I can still do math in my head, mostly. So we've got the following. 101,300 pascals equals the force onto my head divided by the area, which is 0.0314 meters squared. Okay, so I can multiply both sides by 0.0314 meters squared. The meters squared and the pascals combine to become a Newton. Once again, put SI in, get SI out, and we get times 101,300. We get approximately, the force applied onto my head comes up to about 3,182 newtons, which, if I remember the conversion rate correctly, comes up to about 723 pounds. Now, believe it or not, that is how much is being pushed down onto your head. Now, air is lightweight comparatively. Its density, at least at sea level, is a little over 1 kilogram per cubic meter, but that's still a decent amount. And when you start actually climbing all the way up to the full height of the entire atmosphere, having that much air, even though it's lightweight, starts to get a little bit heavy. While this seems unlikely, please keep in mind, this is what we're actually dealing with. This is atmospheric pressure. And if you have questions as to whether or not what I say is correct, once again, we saw that this small little device required 200 some odd pounds to pull apart. And the other thing that I can appeal to is we know that it is the effects and interactions with air, just air, that keep airplanes in the sky. Big, heavy, fast-moving vessels that are filled with a lot of people, and it is just the effect of air that can keep them up in the sky. And this is a peek into how that actually works, at least for some aspects of flight. All right, the last thing that I want to talk about with this is an application into, once again, real-world scenarios. Now, I didn't actually bring any hydraulic systems, but I do have here for part of our robotics program, at least the very small robotics. This is what's called a pneumatic piston, or a pneumatic cylinder. And so, I'm going to refer to this by its more common name, hydraulics, or pneumatics. I may have this misspelled. It may be that the U comes before the E. I can't remember. Both of these are from Greek, and I should remember better. But in this case, hydraulics, hydro for water, basically, and then pneumatics was a reference to air. And so hydraulics and pneumatics are systems that employ fluid pressure to apply forces, often for mechanical advantage. Though not always. Now, these are common things to encounter in many workshops. A lot of times you have pressurized air, compressed air for all sorts of factors, including things like nail guns or rivets or something like that, or even just a cleaning system that you can actually use the compressed air with a blower to actually clear off materials. Not to mention, hydraulics go into heavy-duty equipment on a regular basis. Often when you're using hydraulics, you would actually be using it to amplify the force quite a bit. So in this case, I'm going to talk about, as a brief example, a hydraulic lift. Now, as a heads up, because this has also come up in some of the robotics that we've done, this is why I'm giving you both hydraulics and pneumatics. What we're going to be looking at more likely is going to be hydraulics, in that this one uses a liquid, usually, of some kind. So originally it was water, but now we have a tendency of going with hydraulic fluids for a couple of different reasons, not only chemically, but also to help reduce viscosity and friction effects in there. But it's a liquid, and in short, hydraulics applies when you have a non-compressible fluid. Let's see. Pneumatics, however, is when you're doing something similar, except you're using an air or a gas of some kind, I should say. So air is the most common with pneumatics. They have upsides and downsides. Hydraulics are usually ones that are much more solid on being able to, first off, deliver a very predictable amount of force because of the incompressibility on it. And they can kind of get supercharged because you don't have to worry about compressibility. Pneumatics is a often cheaper, lighter, and cleaner, for want of a better term, way of approaching it. So in robotics, we were never allowed to have hydraulics on the robots because if you spring a leak on that, you end up with that liquid, the hydraulic fluid, getting everywhere, and it's a terrible mess to clean up. If you take a hard hit and you have your pneumatic system punctured, however, you leak some extra air into the air or whatever. Like, it's still a pain, but some of the things that I wanted to point out on that. Air pistons are the sort of things that show up commonly. In fact, I believe the ones on my hood, on my vehicle, my car, are going out, but they're ones that actually extend and help apply a force to hold the hood up when you actually need to get under it. Okay, we're going to look at a hydraulic lift, basically. Now, you can actually reverse this, and instead of having it as a lift, you could have this as a hydraulic press instead. But you're going to see that the ideas behind this can be used in a bunch of different applications. But in short, what you've got is a very small portion of your vessel, and then you go over to a very large portion of your vessel. And let's say that I've got this filled with just water. And we've got it where this can actually go up a little bit more. I want you to imagine that what we've got is basically little discs. And I can push down on one disc and then the other disc can rise up. It's not dissimilar to these, where it's like I start off with this up, I push down, and then this is connected over to another one that could push up instead. In fact, that's one of the reasons why I've got this equipment. I may be trying to build some more hands-on demos with it. But in this case, let's say that I've got something that is, we'll go for relatively easy numbers here. Let's go with something, let's say 1 centimeter, 0.01 centimeter in diameter. Or let's go radius, actually, just to be simplistic on this. So something that is radius of 1 centimeter, that makes this about a little bit under, let's see, because that'd be 2 centimeters. It's a little under an inch. This might be something like 3/4 inch. So a relatively small thing, a little bit smaller than this little press right here, to put it in perspective. And I've got it connected. Let's go over here, and for simplicity, let's say that this has a diameter of, or radius, because I'm dealing with radii. Let's say that this is a radius of 10 centimeters. So 0.1 meter. So we're going to make this a much bigger one, something that's probably more like this. So I've got a small one. Oh, in fact, maybe this is a good idea, where we've got it where I've got this that I can push down here, and it's connected to this one. Here's what I'm going to do. I am going to apply, for me, a downward force, Fa, applied by me. Let's say that I'm going to push down with, I don't know, maybe about 10 pounds worth of force. That might be pretty close to about 50 newtons. So here's what we're going to say. I'm going to push down on this side. Now that's me trying to compress this liquid, and I can push down on this piston, for want of a better term, but I push down on this, not dissimilar to my little hand pump there, and it's going to increase the pressure throughout the fluid. And the thing about pressure is it points out in all directions. It's distributed throughout the entire fluid. That's one of the key things that we wanted to emphasize in this. So we've got the fluid pressure will increase over here. But what we need is to find out how much I'm increasing the pressure. Well, I am applying that force. We could find the pressure on this side would be equal to my force, 50 newtons, divided by the area. Well, that would be pi times 0.1 meters squared. Okay. So if I were to take my calculator, I could see that I've got 0.01 squared times pi gives me 50 divided by this gives me the pressure that I am now applying onto the top of that little piston, which it will pass on to the fluid itself, because you can see basically I push down with 50 newtons on it, it will push down with 50 newtons onto the liquid. So we would have the following. 154, but I'm just going to round it to 3 significant figures. 159,000 pascals. A little bit over 1 atmosphere of pressure. So, interesting that I'm only pushing with about, like I said, maybe about 10 pounds, a little bit more than 10 pounds of force. But we've got such a small area that even that relatively small force can result in a large pressure. Okay, coming over here. This pressure is then distributed throughout the fluid. So the pressure increases here. It then is basically, we're squeezing the entire thing. So the pressure throughout the entire fluid is actually increased by this amount. Now, if the rest of the container walls are rigid, then no movement can happen. If this were rigid, then we would have an increase in pressure there as I push down and I try and squeeze these. But since this is able to actually move, the increased pressure here, we have a greater pressure on bottom, atmospheric pressure on top, and therefore this piston can actually slide up. This is the lift part of this. So I push down with 10 pounds, and then because of pressure, we now find that over here, our pressure is also equal to 159,000 pascals, but that is then going to be an upward pressure that it applies, and that will be equal to our pressure in the fluid times the area over which it is applied. Well, moving that over here, we've got our force up is going to be 159,000 pascals, because that's the pressure that I put it up to, or I'm attempting to put it up to, by pushing down on the left-hand side. The area for this one is going to be pi times 0.1 meters squared, because that's the area of that other piston, for want of a better term. So my upward force is going to be 0.1 squared times pi. Let's see, and I'm going to multiply that by 159,000 pascals, and I get the following. 4,995 newtons, remember, SI in, get SI out. I'm going to divide that by 4.4, and we end up with, this is about 1,135 pounds. I have pushed down with about 10 pounds, and in doing so, I can push up with over 1,000. Now this may sound nonsense, but this is actually how a car jack works. So if you take a car jack to lift up an entire car, which is very, very heavy, usually more than 1,000 pounds, or at least on the order of that, you take a little crank and you push down on it. Many times those are actually using a hydraulic lift in this same way. Here's how you can turn a small force, the amount that you actually have to apply onto that, into a large force to lift your car up. The last thing that I'll mention on this is, because hopefully in your studies you've now studied this, we have amplified the force. This is something called mechanical advantage. This is when you amplify the force. You use a small force and some physics to make a much bigger force. Amplify the force. But does not, I'm going to emphasize that, violate conservation of energy. This is a common mistake that students make. They think, hey, we're getting this much bigger force and therefore the job is easier. Well, it's still going to require the same amount of energy. The same thing that I'll bring up here is, so if we go back to our hydraulics, if I push this down by 1 centimeter, will this go up by 1 centimeter? Well, no, because I'm only pushing a small amount of fluid out of the way. Since we have an incompressible fluid, and I'll leave this as a challenge for you all, you might say, if I push this down 1 centimeter, how far does this go up? What you will find is it goes up based on the ratio of how much we've amplified our force. Now, I've made it 100 times larger, my force, give or take, and therefore, if I push this down 1 meter, this would go up 1 centimeter. And you can also use applying a conserved volume. So basically, find the volume of pushing this down 1 meter, and then apply that onto here for how much volume that would equate to going up. Basically, tall and thin, wide and short is the idea on that. But in this case, mechanical advantage, to reinforce this, does allow you to amplify the force. This is done many times with all sorts of things, including ramps and pulleys and other things. But you will find, just like we had with our example with the hydraulic lift for a car, if you have a very small force, think about how much you have to apply that over. Remember, energy deals with work or force applied over a displacement. So I take the handle up here and I push way down. I'm actually moving, applying that small force over usually at least a meter. And does that result in the car being lifted up a meter? No, usually when you do one of those, small force, big distance, in fact, let's take a look at that. We've got force times displacement equaling force times displacement. We've got my hand applying a small force, so I'm going to do low on this, but over a large displacement. And then what that results in, small force, large displacement, and I end up with a large force over a very small displacement because the car barely ticks up. Energy is conserved, and when you apply the proper applications of energy conservation onto these things, you will find that while we are amplifying our force, we're also setting up that now we have to apply that the amplified force, or we have to apply the smaller force that we've got over a much larger displacement for the large force to end up with a similar displacement. So there are upsides and downsides to these. You can also switch things around where you can end up having use a hydraulic press, for example, where you put in a small amount of force, you amplify that force and use that to make industrial grade equipment that can push down exceedingly, exceedingly hard. At least so long as your container can withstand all of the pressures involved. Okay, so that's all the introductory things that we wanted to get us started with pressure and its applications on fluid mechanics. Until next time.